Ladies and gentlemen, that big noise right there, our class recording has started. So, let me zoom back out here. And up on the screen, you can see a picture of periodic table from your planner. And as we look on the periodic table, right, we said periodic table is a listing of all of the elements that exist in the universe. And we said that elements are unique from all the other elements. They have a different number of protons. It's the atomic number, blah, 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 blah. Yes? And we spent a good portion of last quarter talking about atomic structure, what it's made up of, how it's different, etc., etc. If you look at this periodic table, you'll see that there are listed around 118 elements. This spot here is left blank for reasons we don't have to discuss right now. But so we're somewhere in the range of a little short of 120 elements, right? There are other things out there in the universe, like protons, neutrons, and electrons, that aren't elements, that aren't atoms, right? They behave differently. But all of these elements are unique from all the other ones, right? But if you took a look around just this room, could you find 120 different things? Yeah. Probably, right? And that's just in this room. That doesn't include outside on the grass, or in the ocean, or any of those other places that exist in the universe. My point being, if there's more than 120 things out there, psst, shh, I can hear you guys up here. I can. If there's more than 120 things out there in the universe, okay, that's probably not helping, just saying, you can continue doing it. You're not just disrupting anybody, but it's probably not the most productive thing to do. Just throwing it out there. All right. If there are more than 120 things in this room alone, and that doesn't include all the other places out there, there's got to be a way for these things to make new things. Does that make sense? And that's the gist of our next section, and that deals with chemical bonding. All right? Is it possible to change an element's atomic number? Yes.
Okay, so let's say I have mercury.
Yeah.
And I want to make 7, and I want to turn it from 80 to 79.
So, Stephen says, what if I have mercury and I wanted to turn it from 80 into 79? Could you do it? Is that what you're asking me? Answer? If you turn mercury that has 80 protons into something that has 79 protons, what do you have? Gold. Gold's kind of valuable, right? Yeah, but it's gold. Yeah, but gold is valuable. So if you could turn mercury that's dangerous and will kill you into gold, wouldn't you want to do that? Isn't that like? Yeah. No. Well, okay. So let's talk. Can you do it? Yes. The answer to that question is can you do it is always yes. Okay. Right. And Stephen, this is actually kind of a good transition, right? So, why do things happen? No. I suppose it depends on who you ask, but that's not the answer. It's not the answer I'm going to give you, right? So, the answer to that question, why things happen, is always the same. And if you've been paying attention for the past couple months, you might be able to answer it.
Motion.
Science. Good, everybody. All right, ready? For the 100th time. Okay? Ready? Here we go.
You make it happen.
I get you're dropping the ball, but I don't understand anything that else is that happening.
So, we dropped the ball. Let's go through the questions, okay?
I know, you can drop it more.
So, let's go through the questions, right? I can drop the pen too. The answers to the questions are the same. Why does it happen? Why does the ball fall? Gravity is not why it happens.
You let it energy.
Okay. All right. Why does it happen? Because potential energy is lower on the ground than it is in the air. And naturally, things lose potential energy. Now, in the case of the ball, right, losing potential, or in any case, if we lose potential energy, if one kind of energy decreases, what has to happen? Another one increases, and that's conservation, right? So the ball falls not necessarily because potential turns into kinetic. The ball falls because potential decreases as it goes down. But conservation says it's got to turn into something else. Okay? So why does the ball fall? Because potential energy is lower on the ground than it is up in the air. Okay? So, the answer, now, does the ball always fall? Okay. So, can I make the ball go upward? Yes. Can I make anything happen? Yes, as long as I provide what? Force. Energy, right? Energy is the ability to do stuff. So, the answer to the question of can I do this is always yes. But it's a matter of how much energy does it take. So can you turn something that has 80 protons into something that has 79 protons? Yes. It's really hard to do. You need a lot of energy to do it, but you can. How fast do you have to run? A lot faster than you can run. Yes, Jafar. Nope, could go the other way too. I could turn platinum into platinum. Yep, you can do it. Again, the answer to the question is always yes, but it's a matter of how much. What? How do you do that? We'll do a whole section on nuclear reactions later on. So. No, you take it from another. We'll talk about how that happens. We do a nuclear reactions thing later on. So. Jules, hey. Yes.
Does this conversation have anything to do with physics?
Yes, actually, it's a good way to transition to the beginning part. Okay.
When you say like energy,
Yep.
like it's like a broad.
It's a very, very broad term.
What type of that?
Well, okay, that's a good question, Jules. Let's transition to that, okay? Hey, can we stop it, please? All right? You guys, there's a certain part we have to get to, all right? I don't want you guys to be behind already in the first day that we came back, okay? So, Jules, question. What kind of energy, right? Energy is a broad term, very much so, right? But when we talk about energy, we always can relate it back to it's the ability to do stuff. And stuff is a very broad term too, but that's kind of how does energy apply to this situation, okay? The ball is gravitational potential energy. Where is it in relation to the Earth, okay? When we talk about atoms, we spent a large amount of time talking about electrons and placement of electrons and stuff like that. If I give you a Bohr model, if I say Bohr model, do you have a picture in your mind? Okay. So we said, what happens to electrons as they move farther and farther away from the nucleus? Can you answer that question, or do you want somebody else to answer that question? So, more potential energy. That's not gravitational potential energy, it's what we call chemical potential energy. but it's another type of potential energy, the ability to do stuff, okay? So, let's go there, okay? The whole point of this conversation being, here's the elements, but there are more things out there in the universe than there are elements listed on the periodic table. So where do all those things come from if these are the building blocks? And that's when we get into chemical bonding. All right? So, chemical bonds, by definition, are an attractive force that holds atoms together. That joining together of these atoms results in something new. A new substance with different properties than what the individual elements had by themselves. Okay? So, let's put the pieces together, right? Why does bonding happen? One word answer can answer it.
Gravity.
Energy. Okay? Specifically, what do we want to happen to the energy? Okay? Formation of chemical bonds involves energy, specifically a decrease in energy. Bonds will form if atoms have lower energy together than when they were separated from one another. The answer to the question of why is always energy. The ability to do stuff. And more often than not, it's because there's less energy than before. Okay? So, why do bonds happen? Because atoms are looking to get rid of that potential energy that they have, and they do it by bonding with something else. And you'll see we've talked about this before already, and there's going to be a lot of things that come back that we've talked about already too, right? As a result, we generally call bond formation an exothermic process. You know English. Tell me about an exothermic process.
So does that mean like out?
Out is
Thermic
exo,
means heat.
thermic means heat. So, what happens when atoms bond together?
The heat extracts.
They release heat. Just like, it could be an explosion, but it could just be something gets warmer, right? An explosion is an extreme example of an exothermic process, but it is, right? A fire is an exothermic process. The fire itself is energy, energy being released. Just like when this ball goes from high to low, its potential energy decreases. But a decrease in potential energy has to be accompanied by an increase in something else. In the case of this ball, potential energy goes down as kinetic energy goes up. In a chemical bond, chemical energy goes down, but heat, and sometimes light, depending on what kind of reaction it is, will go up. Thermal energy would go up. Or it could be light too, like in the case of a fire or an explosion, like you see there's light and heat given off, right? That's how you see the explosion. But like in the case of like hand warmers, you know, like those chemical hand warmers, those just give off heat. But it's still the same idea that the atoms in there are joining together with other atoms, lowering their energy, but they have to get rid of it somehow because of conservation, and they give it off in heat. Okay? Bonding deals with valence electrons, electrons that are in the highest energy level. And hopefully that sounds familiar, right? We spent a good amount of time talking about electrons, what are valence electrons, and stuff like that, hopefully. All right, good there. Good there? Okay. Next, let's go back here and do some review. I'm going to do the heavy lifting for you guys, though, okay? Ready? All right. Here's your periodic table. Here is oxygen. Okay? Okay? So, first, what is that?
Electron configuration.
That is oxygen's electron configuration. Right? And based on oxygen's electron configuration, how many valence electrons does oxygen have?
4. No.
8.
6. Yeah. 6.
So we've got 4, we've got 6, we've got 8.
1.
Valence electrons. Hey. All right.
1. 4. It's 8.
I agree.
It's 8. It's a stable. It's stable. Why would it be gaseous?
All right.
It's atomic.
Oxygen stable?
Is it stable?
We use oxygen to launch rockets into space.
You know what? It's 1. It's 1. Tell us.
All right. So I'm trying to tell you. All right. So by definition, valence electrons are electrons in the highest energy level. What's the highest energy level that I have written here?
4.
2p is the highest orbital. What's the highest energy level? The second energy level. Some are in s orbitals and some are in p orbitals, but how many electrons are in the second energy level?
Oh,
6.
yeah, but I'm dumb. Yeah.
Oxygen has 6 valence electrons. All right, next.
Just all doubted me.
We always will doubt you.
Yeah, I did. You liar.
You said 8. 6. 6. 6. Jamar, how many valence electrons is this?
All right, so there is the electron.
Why do you write it over the yellow?
That's okay. Right now I'm just writing electron configuration. All right, so hey, there's the electron configuration for sulfur. How many valence electrons does sulfur have?
2 and 4. 6.
So it's a 2 and a 4. So sulfur has 6 valence electrons. Okay. Okay, let's go here. All right, so there's the electron configuration for magnesium. How many valence electrons? 2. Okay. All right, all that sound familiar? Yes?
Yeah.
Okay. So,
Wait. Don't like we draw out like the electron shell. Doesn't like 2, 8, 8, 2. I know like a bunch of different.
when we look at, yes, because we keep adding like p orbitals and d orbitals and stuff like that. Okay? We're gonna look for patterns here to begin with. Okay? So, yep. All right. So, because hey, this is being recorded, by the way. Good. Because valence electrons are what we're concerned with, we use Lewis structures to show the representation of that element and its valence electrons. And we do that by drawing the elemental symbol and then valence electrons represented by dots. We don't have to break into. We don't have to break into conversation. Why do we have to talk every single time? Everybody.
That's the only time I actually didn't talk.
Oh, now you're not done, but you're talking? I see how it is. All right, so let's start off with lithium.
Like that.
Okay. There's the electron configuration for lithium. How many valence electrons? One. And I think if we hopefully remember, we said that elements that are in the same family have the same number of valence electrons, right? So any element in this family will have one valence electron. When we come back, and you'll see that on your outline, this is the first thing we come across, okay? So a Lewis structure for lithium would look like this. It has the elemental symbol, and then it has the number of valence electrons. When we're dealing with bonding, we don't care about all the other electrons, we only care about the valence electrons. So lithium's Lewis structure would look like this. Okay? Good there?
Like, I already know how to do this, but like, does it matter like where like the dots are?
So, does it matter where the dots are? No. Okay? But, Pat, you'll see...
Or like, I know like you have to fill like all of them up first.
That's
and
the
then
goal.
Go back, but like, does it matter like where you place it?
No. And we'll talk about that in just a second. So, okay. Laura, go ahead.
In a box.
Oh, sorry. The box is just my... That was... You don't need to put the box. No. So, yeah, that was just where I got it from. And stuff like that. I believe the next one that's listed on there is oxygen, right?
Yeah.
So we've already established oxygen has how many valence electrons? 6. So oxygen's Lewis structure would look like this. Okay? Again, don't worry about the box. Okay? But Pat, to more specifically address your question from before, okay? Generally, when we draw Lewis structures, we think of it kind of like having 4 sides around the symbol. We generally put no more than 2 dots on each side, and then we'll kind of like fill it up like, if I was drawing oxygens, I would put the first dot here. Oh, that's not what I wanted to do. I'd put like the first dot here, then the second dot here, then the third dot here, 4th, 5, 6. But really, it doesn't matter. It doesn't matter where the open spaces are. Now, the one thing that we will do, okay, one thing that you won't see, generally you won't see like 2, 2, 2, and then nothing on that side. We try to pair, again, just like real electrons, we try to spread them out as much as possible before we start pairing them up.
Like that one thing, like not the electron configuration.
The orbital diagram, very similar.
Like you have to draw like
Very
one arrow and then,
yeah, we try to do that as much as we can. Is that your question, or? Well, you tell me. What's the next element that's listed down there?
Fluorine.
Fluorine. Fluorine is in which column? 17. All right. And hopefully you remember, but in case you don't, okay, let's go back here. We're going to make this a little bit easier by doing this, okay? Here's my periodic table. For our unit on bonding, we are basically going to get rid of that part of the periodic table, okay? So we're going to deal with column 1 and column 2, and then columns 13 through 18. Okay? From a valence electron standpoint, we've already established how many valence electrons do elements in column 1 have? 1. How many valence electrons do elements in column 2 have? 2. And then we established that elements in column 16 have how many? 6. Right? That's not a coincidence. It just goes right along. Okay? Okay? And that's the number of valence electrons that elements in that family have. The next one that's on your outline are fluorine, or the next 2 on your outline are fluorine and chlorine, right? If you look on the periodic table, what do you see about fluorine and chlorine?
In the same group.
They're in the same group, meaning they have the same number of,
Valence electrons.
and that number is 7. And so we draw
7.
Lewis structures for fluorine and chlorine that look like this. All right? Notice, all right, Pat, kind of going back to your point. For the fluorine one, the single electron is on the right. For the chlorine one, the single electron is on the left. It really doesn't matter. All right? You can make a top, you can make a bottom. It really doesn't matter. There's no necessarily right way or wrong way to draw a Lewis structure. It's a tool to help you figure out valence electrons and what's going on. Okay? Okay. The next one that's listed is neon, right? Neon is in what column? 18, right? And that means it has 8 valence electrons, and it looks like that. Okay?
So, boron would have 3 and aluminum?
Boron would have 3, aluminum would have 3.
Because I thought we like,
It's really easy to prove.
you know how like, carbon, nitrogen, oxygen, phosphorus, substance, aluminum are on the same page.
Carbon and nitrogen are not in the same column.
Alright, let's say group 18.
Okay, group 18.
What? No, it doesn't work.
All right. All right, so the last Lewis structure we drew was neon. All right? Neon's in group 18, but group 18 we gave a special name when we were identifying families on the periodic table. Those are noble gases. Noble gases have one very distinctive feature. Do we remember what it is? They are gases, right? But there are other elements that are gases that are not noble gases. Okay. Well, the property is, what don't they do?
React.
They're not very reactive, meaning they don't form chemical bonds. Why?
They form ionic bonds.
They have how many valence electrons? 8. And we said 8 is the magic number when it comes to valence electrons. So, are we ready? We got to make some like word associations here. We got to apply things to different situations. All right, ready? Time 374. Okay. So, now I haven't really time. All right. Why does that happen?
Potential energy.
Lower potential energy. How does it happen? Somebody said it. Well, no, that's why. Gravity. I heard somebody say it over there.
I know, it's funny.
All right, hey. Why does it happen? Potential energy goes down. How does it happen? Gravity. Chemical bonds. Joining of two atoms together. Why does it happen? Energy. Right? Lower energy. But how does it happen? Valence electrons, specifically, what's our magic number for valence electrons? 8. 8 valence electrons is how chemical bonding happens. All right? So, valence electrons, chemical properties. The number of valence electrons determines the chemical properties of an atom. And when we say chemical properties, that's a fancy way of saying what? What do valence electrons do? What are valence electrons responsible for? Reactivity, or that's a special, that's kind of a fancy way of saying. There's a word I want you to say.
Guys, tomorrow's Tuesday.
Jesus.
Look at the top of your outline.
Ionic bond.
Okay. So, chemical properties. When we talk about the chemical properties of an atom, that's a fancy way of saying what will it bond with and what won't it bond with. Right? Atoms are trying to get to 8 valence electrons, and they will take the shortest route to get there. And we refer to that as the octet rule. Like, because you know what an octopus is and an octagon, right? Okay. So we refer to this as the octet rule. Right? But there are different ways we can get to 8, right? For instance, if we go back to these right here, okay, here's magnesium. We said magnesium has how many valence electrons? How many valence electrons does magnesium have? I'm circling it. It has 2 valence electrons. So, to fill up level 3, it would have to do what? It would have to gain how many? 6. But it doesn't do that. Why? Because instead of gaining 6, what it does is it drops those 2. Now, the highest level is what level? It's level 2, but how many electrons are in level 2? 8. And so the highest level is full, even though it wasn't the level that it started with. Jules, go ahead.
So how is that possible that it just like it works?
Why does it do that?
So I know why it does that, but like how does that happen?
Okay, that's what we get into tomorrow. That's by ion bonding, all right? So, continuing on with our outline. Getting to 8 could mean gaining electrons and it could mean losing electrons. Because when you look at the periodic table, as you go left to right across the periodic table, starting in column 1, going to column 2, then 13, 14, 15, what happens to the number of valence electrons as you go from left to right? The number of valence electrons increases until you get to column 18. Because then when you go to the next number, it's back in column 1. And then it has how many again? I know, I always do that. So yeah, there should only be one. There should only be one O in there. Right. So when you look at valence electrons, right? 1, 2, 3, 4, 5, 6, 7, 8. But then it goes 1, 2, 3, 4, 5, 6, 7, 8. So if you have 7, getting to 8 means going up 1. But if you have 1, getting to 8 means going down 1. All right?
No, we have to finish this page.
So,
Atoms
atoms will gain or lose electrons to have a full outer shell or a full valence shell. Metals. What side of the periodic table are metals on? Left-hand side. That means they have a small number of valence electrons. Hey, whoa. With all the time you wasted today, we're finishing this. Metals lose valence electrons so that their electron configuration comes like the previous noble gas. Why are noble gas electron configurations important? How many valence electrons do noble gases have? 8.
They're stable.
Non-metals will gain electrons to become like the next noble gas. Again, noble gases are important because they already have 8. So, if you look at small atoms like lithium, lithium has 1 valence electron, but if it loses it, because it's a metal, it only has how many? It only has 2. But those 2 are in the first energy level. If you remember, hopefully, there's only 1 orbital in the first energy level. Remember we went from 1s straight to 2s? So this level is full with 2 because there aren't any other ones.
Wait, so when you lose, when loses that valence electron, does it become a noble?
No. It becomes something, so the question was, did it lose that valence electron? Does it become a noble gas? The answer is no. It becomes something that we'll talk about tomorrow. Okay?